Alrighty, time for another coding challenge, daily challenge. Looks like it's part 1, so it's gonna be maybe a hard one coming up to end the month, maybe. Alright, maximize the number of target nodes after connecting trees. There exist 2 undirected trees with n m nodes. Okay. And distinct labels of range 0 to n-1 and 0 to n-1 inclusive, respectively. We were given 2 integer arrays edges of length n-1, n-1, where edges I equals a, edges I is a, b, indicates an edge between nodes a, b. So it's the number of edges is 1 less than the number of nodes. So basically every node is probably connected to yeah. Okay, and similarly for edges 2. We're also given integer k. Node u is the target of node b if the number of edges on the path to uv is less than or equal to k. Node u is target to node b if the number of edges from u to v is equal to k. Node u less than or equal to k. Note that a node is always target to itself. Return an array of n integers answers, where answers I is the maximum possible number of nodes target to node I of the first tree if you have to connect one node of the first tree to another node of the second tree. Note that the queries are independent from each other, that is, for each query you remove the added edge before proceeding to the next query. So you're adding an edge is the number of edges. Okay, so let's just clean it up here. So you have nodes n and m nodes. Those aren't values that are given. So just the length of the array is the n and m. So there's like maybe 4. There's 4. The length of the array is n. So n is 4 here, and m is 7 here. And you have 4. If you have 4 edges, okay, anyways. So edges between 0, 1, 0, 2, 2, 3, and 2, 4. 0, 1, 0, 2, 0, 3, 2, 7, 1, 7, 1, 4, 4, 5, 4, 6. K equals 2. So you're dealing with, and you have answers at I is the maximum number of target nodes from node I. So from like node 0, it's the maximum number of target nodes to node I, the first tree, to connect one node from the first tree to another node of the second tree. Okay, so it's how many nodes you can connect a node from. Okay, so for I equals 0, connect node 0 from the first tree with node 0 from the second tree. And at that point, 0 is going to be within 2 of 9 nodes. So like node 0 is going to be within 2 of obviously 0 itself. 1, 2, 3, 4. Like hopping from like 0 to 3 is going to be 0, 2, 3. So it's within 2. And then hopping from 0 to 4 is like 0, 2, 4. So it'd be also 2. So 0, 1, 2, 3, 4. 5 is out of reach, I want to say. And 6 is out of reach. 7 is in reach. So 0, 1, 0, 1, 2, 3, 4, 7. That's 7 nodes. That's 0, 1. Oh my yeah, 0, 1, that's 2, 2, 3, 4 is 5, 7 is 6. So there's 6 nodes there, and then from the other tree you can also reach 1, 2, 3, so that's 9. Okay, so this is tree 1, and this is tree 2. Connect node 0. Okay, so this is tree 1. Shouldn't tree 2 be, isn't this kind of swapped? Shouldn't this be called tree 1 because node 7 is on it? Yeah, I think the images here are reversed or in the wrong order, mislabeled, whatever. So if you think about 1, if you connect node 1 with node 0 here, is the maximum number of target nodes from node I of the first tree if you connect one node from the first tree to another node in the tree. So if you connect node 1 to node 0 here, I guess on the first pass, it was like this is tree 1. So 0 goes to 1, 2, 3, 4, 5, 6, and then if you connect it to here, then this 0 is 7, 8, 9, and that's going to be the 9. And if you connect node 1 to node 0, within 2 would be 1, 2, 3, 4, 5, 6, 7, and connect to 8, 9, 10. That's not correct. This should be 7. Connect node 1 from the first tree to node 0, the second tree. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Huh. Ooh. It's only 7. Connect node 1 from the first tree to node. Am I thinking about the wrong nodes? Is edges 1? Edges of 1, A, B indicates there's a node in nodes. Oh my god, I'm misreading it. So I'm looking at this through this, like I somehow separate this as one tree, and like this, I read this as a new line for some reason. Oh my god, that's so stupid. Okay, 1, 2, 3, 4, 5, and then connect here 6, 7, 8, 9. Okay, that's right. And we connect here from this 1 to this 0. It's like 1, 2, 3, and then 4, 5, 6, 7. I see. So I think I don't see what the point is of the second tree. So how should I phrase this? It looks to me like you would always connect to the same node in the second tree. Why would you connect to a different node? Connect node 2 from the first tree to node 4 the second tree. Node 2 here to node 4 here. So then you go to, oh, are you trying to hit different numbers? So if you go 2, so 1, 2, 3, 4, 5, 6, 7, 8, 9. So it's 9 in there as well, but why would you connect it to 4? Because you could connect it to the 0, no? Same amount of things that you would get from it. 1, 2, 3, 4. Actually, why? Yeah, so like if you connect to 0, it's also 1, 2, 3, 4. So I think you should always be able to connect the node to the same node of the other tree, because there's some optimal amount that you can get from the other tree, and it's the same each time. The same increase in the number of nodes that you get. So it just depends on how many nodes that you have from the first tree for that given number, connected to that given number, and then some fixed amount from the second tree based on like the maximum that you can get from that tree. The maximum of any node connected through K from that tree. Yeah, so it's like all connected to the first node. Okay, so I'm going to start by assume, so this is based on my logic, my reasoning here. I'm going to assume that the second tree connection will always give a fixed maximal amount of additional kind of reach. So, and only and the only variable is how much reach is from node X in the first tree to its neighbors within K range. Okay, so I need to figure out two parts for each node, what the reach is in the first tree from that node within K, and then for the second tree, what the number of things that you can increase that reach with, or increase the count by. So let me start by doing that in the second tree. So determine max reach from any node in second tree. This is going to be a fixed amount. So I have a list of edges, and I probably prefer like a different version of that graph, the adjacency list. So graph 2 is going to be a default dictionary. I'll optimize that or change that structure later on of lists, and for every A, B, and graph in subgraph, in edges 2, then graph 2 of A dot append B, and graph 2 of B dot append A. All nodes are connected, so it should be fine. And then for how would I want to do this? Is there a way to quickly calculate this? So I don't think there's any cycles in this tree. I doubt there's any cycles in this tree, but I could be wrong. If there were a cycle, then what would happen? If all nodes are connected, if all nodes are connected and there was a cycle, then it would imply that you can't have a number of edges less than the number of nodes. Like if there's a cycle, then there has to be like, and there's like, let's say 3 nodes, right? You need to have 3 edges. If there's 2 nodes and there's a cycle, then you have 2 edges. And because the number of edges is less than the number of nodes, then there can't be a cycle. So I think with that logic, let's say max count is going to be 0 for every a for every node in the graph. Let's say the count of this node is starting at 0 for every neighbor of the node. For every neighbor of the node. So looking through the list connected to that node. I think you just do a nested for loop here, and then for every neighbor of that neighbor. So let's say the count is equal to the length of the number of neighbors. Length of the neighbors. Length of the number of neighbors for that node. And then for every neighbor, count plus equals the number of neighbors of that node. Length of the graph of that neighbor. So here, node is shorthand for neighbor. / adjacent node. For every so then it would double count certain things. So for instance, if you go from 0 has 2 neighbors, or let's look at tree 2. Go from 0. Actually, because I'm thinking about tree 2, oh, I need to do this for k, right? This is for k length. If the k length is 2, then actually when you connect to the second node, then it boils down to 1 away from any node, because you already connected you already used one connection from going from tree 1 to tree 2. So therefore, what you want is from any node, how many nodes are k minus 1 away from that node. And that's your max count. This could be many layers, so this could be many layers. I don't want to do this multiple times. This could be many layers, and I don't want to do this multiple times. Like if I do 0, and then 0 adds on to, let's say a stack, 2, 3, 1, and then when you process each element of stack, you add on to its neighbors. That calculation I'd only want to perform once, because if I perform if I do 0 for that, and then I do the same process for 2, and I do 2 add on to its own stack, 0, 3, 7, that's just a bunch of redundant calculations. So how many away from each node starting at that node? So how many away from each node starting at that node? So 0, there's these 3's that are 1 away. 2, there's these 3 that are 1 away. Do you really have to do a new search each time? Do you really have to do a new search each time? Seems a little ridiculous. think maybe you can detect leaves first and iterate backwards from those leaves. Because there has to be some leaf nodes to this tree that are only adjacent to one node. Now, it could be a tree very simple like this, where 0 and 3 are the leaves, but here like 7, 3, 5, 6 are leaves, and you say that the reach of them is initially, let's say, 1, right? Because there's only one node adjacent to them. And then you go backwards and say that this one, any adjacent one, is 1 plus the number of leaves. Interesting. So you start with your leaf nodes, you process each leaf node. When you process the leaf node, you increment the count of the connections of any nodes from there, and you put those numbers into the queue or stack, and then when you process that, you increment things, and if you have already seen the node, then you don't need to process it. Okay, so I think, okay, so let's say I need to figure out this the leaf stuff. For every node in graph, I'll say leaves is, let's start with just a stack. Here I'm going to add any leaf nodes, which is has one neighbor, and here neighbor is shorthand for this, to stack. And this is kind of the process stack, the stack of nodes I'm going to process. There's my neighbor to stack. So if the length of the number of neighbors of this node is equal to 1, then stack.append this node. And then I'm going to also have a way of tracking the number of connections. Yeah, connected is going to be 0 times the number of nodes in tree 2, and I should probably make a variable for that. So n and m were the number of nodes, so n is equal to the length of edges 1, and m is the length of edges 2. So connected for tree 2 is going to be, I might need to call this connected 2 for tree 2. But anyways, if the number, and then I'm going to say that I'm going to start by saying the connected amount for this node is equal to 1. And then as I go through each, as I go through the stack, node.stack.pop, node equals stack.pop. I think this might be a queue actually, because I want to process all the, I'm going to add more stuff to the stack, but I want to process all the leaves before I process any follow-up. I want to process all the leaves before I process any follow-ups. Yeah, so I think this should be a queue. I'll call this a deck for a double-ended queue. So add any leaf nodes to the queue, and queue dot append this node. Okay, so then while there's a queue, then I'm gonna do queue dot pop left to get the leftmost node. I also need a scene set to make sure that it's possible that, like, for instance, if I process certain leaves that are connected to the same kind of parent, and from 5 I would add 4 to the queue, from 6 I add 4 to queue. I don't want to process 4 multiple times, so I'm going to have a scene set, and if I already seen the node, then I know that I processed it. Or maybe call it processed. So if the node isn't processed, then skip the node, otherwise the node is added processed. And what happens would be for each node, I increase. Okay, so for each node, what do I want to do here? Each node is connected to one node originally itself. So I can say 5 increases 4 by 1, and 6 increases 4 by 1, in which case 4 becomes 2-ish plus 2. And then how would that work? Like, if 4 is, let's say, 3 nodes from the ends, then what does that imply about 1? 1 is, it's not like 1 is 3 nodes from the end there either. So if I want to say k is 2, the leaves go inward by 2. Leaves go inward by 2. So this becomes something within reach of 2 of the leaf nodes. Huh. That doesn't really solve the issue. The question is how to determine how many nodes are within k of any node. I guess this is the same problem that I'll eventually do on tree 1, but tree 2 is k minus 1 and tree 1 is k. Okay. How many nodes are within k of any node in a given tree? An efficient way of doing that, because k could probably be pretty large. Yeah, k could be 1,000. And the nodes could be like 1,000. So this should actually be fairly simple in terms of, like, seems like a pretty common problem. What's the maximum number? What's the maximum that you can get within range of k of a certain node for any node in the tree? So you know that for leaf node, the leaf node would depend on, so maybe you go something like, for each node you slowly iterate. Does that work? So you say that for k equals 1, each node is 1 away from itself, so you start with that. And then for k equals 2, for each node you go through its neighbors. And then for each node you go through its neighbors. It's just a bad idea, I think. For each node you go through its neighbors. Oops. Each node you go through its neighbors. No, there has to be some faster way of doing that. Okay. So let's say can you start with any node and try to figure it out? So for node 0, so node 0, you add 2, 3, 1 onto a queue. And then when you process 2, you add things you haven't seen. So you have already seen 0, so you add 7 to the queue. 3, you add, then the node becomes really large. So if you say node 0 has 3 things that are 1 away from it, and you know that 2 has 2 things that are 1 away from it, and 3 has 1 and 1 has 2, could possibly determine that it's like going to be the neighbors would be like 1, 0, and 0 that's not 0. But then you'd need to then you need to do something, you need to do more iterations of that to find so from a given node, how many are within k of it? From a given node, how many are within k of it? So you can clearly tell how many are 1 away. It's just so, it just seems like it takes so long to find it for every single node, for every single k. Alright, there has to be some idea that I have here. So process it simultaneously, process 0 through the number of nodes. Each time you process a node, you look at what So for instance, this one where k is 1, well this one, k is 1, and this, yeah, to any node, the second tree, it's just k is 0. I just add 0. But if its k is, let's say, 2, so from here, from any node, it's 1 away. Feels like this should possibly be dynamic programming. Like the number of nodes that are 1 away from a particular node depends on the number of nodes that are k minus 1 away from that other node, maybe. But it doesn't seem like there's a particular order that you should be going through the nodes. The order kind of matters. So, can you start the order by your leaves? Because your leaf is going to be, your leaves are going to really just depend on the leaves are just really going to depend on the things that are adjacent to the leaves. So if k is 2 and you have a leaf, then it's really k minus 1, or the connections to the non-leaves of your one single neighbor. So from 7, and say k is 2, then it's going to be 1 for the node itself, 1 for the single neighbor, and then the number of other neighbors of this thing that are not 7. Maybe that's it. But how do you chain it further? So when you reach a node, how do you chain it further? So let's say you reach 2. 2 would chain onto 0 the number of nodes that are connected to 2. 2 would chain onto 0 the number of nodes that are connected to 2. Like I'm kind of imagining, let's say you had a really big tree. Let's say that you had k is 5. So we kind of want to dive deeper into the tree, 5 iterations. And then on the next iteration, like some other node that's like 6 deep in the tree, you want to remove the leaf nodes at that point. The leaf nodes from the path up to there. So it's like you almost keep track of a list of things, a list of the number of nodes at a certain depth within the chain. So for instance, the 4 here, it recognizes that there's 2 leaves here, so that when it goes further in, and it's already 5 in, then the next node that connects it to would remove, subtract 2 from the count of things that are within that reach. Interesting. So for each node, I keep track of the number of nodes that are x away from that node. So I start with leaves, I go to the neighbors of the leaf and say that I increment by 1 the number of nodes that are 1 away from it. And then when I process these ones, I go to the next one, I increment by its value the number of nodes that are I kind of need both. I'd say that because if there's one next to it here, I would say that the number of nodes that are 2 away from this thing is increased by 1, and the number of nodes that are 1 away from it are increased by 1. Okay, I think that solves the issue, or could solve the issue. So for each node, I need to track how many nodes that are x away from it. So for each node, track number of nodes that are x away from it, where x could be anything less than or equal to k. Okay, so it's going to be connected. Oh boy. Is that going to be n squared? That's 1,000 times 1,000. I guess that's still that's still pretty large. Okay, but I think that might be necessary. So it's going to be 1,000 connected. It's going to be 0 times how many k is, or maybe k plus 1. I'm going to say k for now for each node in M. So I still want to start with my leaf nodes because I know that they're going to be. Do I want to start with 1 for each node actually? Because it's connected to itself. Yeah, actually I think I start with 1. So I do want to find the leaf nodes. Okay, so remove that part. Processed equals set. Yeah, that's fine. So while node is, you haven't processed the node yet, then you add the node to the things that you've processed pretty much. And then I want to limit this to the neighbors that haven't been processed from this node. So for every neighbor in the graph of the node, if the neighbor has been processed, then skip the neighbor. So from leaf nodes should just be connected to unprocessed neighbors at the start. And then if the neighbor hasn't been processed, then I want to go through all k values, possible values. Oh shucks, this is not right. Connected is it shouldn't be 1 for all values of k. It should be just 1 for the k equals 0. So this is 1 if k I can't do that. Okay, I can't make an if statement there. Should be 0 times k and then I guess for I in range of k, I in range of k, yeah, connected of 0 connections for the kth node, no, for each node. Okay, so for node in range, m for each node connected with that node at 0 range is going to be 1. Okay, so process if the neighbor has a process, then has already been processed and keep on going. And I think I do something like for every value of range. So range and no, so let's say away in range of k. How far is away? If the connected of this node of this range is equal to 0, then I'm going to break. Otherwise, I'm going to say that so for each neighbor, update the neighbor for the range plus 1. Update the neighbor range plus 1. I think that's right. So things that are one away from this thing is going to be, so 2, the number of things that are 1 away from 2 is going to be the number of things that are 2 away from the neighbor. So if there's nothing that's far away from neighbor, then there's nothing any further away from neighbor. For each neighbor, I wonder if this should be for every away amount rather than for every neighbor. For every neighbor and every away amount, or for every away amount and every neighbor. I think it might be the other way around. I think I'd prefer it to be for every away amount and then for every neighbor, update that neighbor for that away amount. So there's going to be a break and continuing either way. So if I just keep the neighbor. Okay. For every neighbor, for every away amount, if connected of that node is with the away amount is not 0, then just break. Otherwise, connected to the neighbor for the way amount plus 1 plus equals connected to the node this away. So connected to the number of things that are like 1 away from 7, which is like, or 1 away from node 2, which is like 1. That number increments the number that was 2 away from 0. But if there's something like 4 here, there's 2 things that are connected 1 away from 4. That means that there's going to be 2 more things that are connected that's 2 away from 1. And that could include itself. Does that include itself? Yeah, everything starts out connected 0 away from itself. So I think that might be, I think this may be k minus 1 because you can't be going out of bounds in that fashion. Okay, I think I just want to print out, oh, I need to add neighbor to the queue. If it's in process, continue, otherwise process. Queue needs to add this neighbor, or append is a kind of a list ish, and then it goes through here. The neighbor becomes the node. The node is checked to be processed again, adds it here, and then process the unprocessed neighbors of that. Okay, let's go ahead and see what this came up with, if it's correct. Oh, I should probably, this is probably going to give me an error here. I'm returning a number, I think. Yeah. And this is not like a medium problem, or this is definitely a harder type medium problem. For every node in graph 2, oh fuck me. Okay, I'm just gonna call this hold the graph 2 up here, graph by itself down here. Did I call it graph by itself here? I'll call this graph 2 then. Oh, queue is not, no, it should be deck. Double-ended queue. Index out of range. When is this going out of range? Interesting. Let's go ahead and just print out, let's say the node and the way, and the node, the neighbor, and how away that I'm processing it now. So I'm trying to do node 7, neighbor 2, away 0. Node neighbor, node 7, neighbor 2, away 0. Huh, really? I guess 7 is a leaf. Okay, yeah, 7 is a leaf. So the 7 is starting. And why is this out of range? Oh, actually, I think, yeah, I think this might be incorrect by, well, no. The length of this thing should be m. The length of it should be m. So the number of nodes should be m. The number of nodes should be m. 0, 1, 2, 3, 4, 5, 6. That is 1, so 7 nodes. I guess if you have 7 nodes, actually that's kind of weird. There's this 2 trees with n and m nodes. If you're going from 0 to m minus 1, that's m values. So it's m values. And so there's 7 values here. But the nodes are actually, there's 8 nodes. I think. Why am I getting confused here? So 7 is the number of 0 through m minus 1. That's m values. There's m things inside that array. No. No, I think that's wrong. So if it goes to 0 to 1, 0 to 1 is m plus 1. So if 1, oh my god. I guess I'm so confused. Normally it's not m minus 1, that's inclusive. So this counts as 1. So if m is 2, 2 minus 1 is 1, 0 to 1 is 2. So there's 2 values here, where those values are 0 and 1. But there's the length of this thing is 2. So the length of this thing is 7. So is there a missing number here? 0, 1, 2, 3, 4, 5, 6, 7. There's 8 nodes. There's 8 nodes. 0, 1, 2, 3, 4, 5, 0, 1, 2, 3, 4, 5, 6. So if 6 is equal to m minus 1, then m equals 7. But there's 8 nodes. I think this problem is described incorrectly, I want to say. There should be like m nodes where it goes from 0 to m minus 1. Oh, these are the labels. These aren't the edges itself. Okay. Okay, the number of edges is m minus 1. So 7 is m minus 1, so the number of... Okay. I'm just stupid. Okay, so let's see what printed out here. So the number of things that are connected. Okay, so from node 2, okay, I think I need to actually separate this out. From node 0, things that are 1 away is 1. Things that are 2 away should be 3. That is incorrect. Yeah, this seems incorrect. From node 0, things that are 0 away is 1. Things that are 1 away should be 3. The most of this 2. So from node 1, things that are 2 away. do make this plus equals for every range. So let's do, what is my, I'm only processing 3. So the leaf nodes are 7, 3, 5, and 6. So when it processes 3, it's going to say 0, there's 1 away from it. When I process 7, it's doing 2, 5 is doing. Okay, yeah. It still needs to do the other stuff. And then it does another iteration where it does 2. Wait. Actually, what's going on here? 3 adds 0, 7 adds 2, 5 adds 4, 6 adds 4. And then the next iteration does 0, 0 again. Okay, what's going on here? Let's say popping this node number. So it does 3, 7, 5, 6, those are leaves. 3 added 0, 0, 7 added 2, 5 added 4, 4 added 1. That should have been right, actually. Number of things. So 3 added 0. Okay, let's go ahead and also, so after doing all this, I'll say print done node and the connections after this. So it's done 3. It should say the 3. Actually, I wonder if it should start with k equals 1 rather than k equals. No, actually it's fine. It starts with k 0 and then increments the things that are 1 away. So actually, is this correct? No, this should say 0 should say 1 and 3. Okay, so let's go this. 3 is going to say 0 is connected to one thing. And that's that. That's correct. Does 7 and should say that 2 is connected to one thing, 1 away. So that is fine. Does 5 and says 4 is connected to one thing, and that's fine. It does 6 and says that 4 is connected to 2 things now, it's fine. And then it does 0. And 0, it should say that, oh boy. So when it does 0, it should say that it should say that 2 is connected to 0 hasn't been processed, 2 hasn't been processed. and 1 hasn't been processed at that point. And then if it says that 0 contributes 2 here, say 0 contributes 2 here, or 0 contributes to the 2 here, 2 still needs to contribute to the 0 here. Huh. But then it's kind of a cat and mouse game. So does 0 contribute to 2? So say 0 contributes 1 away, and 1, 2 away from 2. So that means that 0, 1, 2. So the neighbors, so 2 becomes 2. Yeah. The neighbors of 2 becomes 2. I don't think I can skip out when you process a thing. Yeah, I think when you process a thing, when 0 is processed, it doesn't know how many neighbors it actually has necessarily. Because 0 can go to 1, or 1 can go to 0. Fuck. So 0 doesn't have an accurate count of things that are like 1 away from it at that point. So if it tries to increase its neighbors, even if it had the correct order, it doesn't have the correct information. Huh. What to do, what to do, what to do. So it feels like you do want to start with your leaves. So if you start with your leaf and you go inwards, start with your leaves and you go inwards. And then go from those leaves inwards. You're guaranteed to be, yeah, don't necessarily hit this. You're not guaranteed to have fully accounted for everything. Maybe this is another one of those cases where you only process yourself if all your leaves have, all your neighbors have, no. So you don't necessarily know which neighbors you should be going for. So like 5, it can guarantee that it should be processing itself because none of its neighbors, like it only has one neighbor. Only have one active neighbor, I guess. One unprocessed neighbor. Only process yourself if you have only one unprocessed neighbor. Interesting. So when 7 processes itself, it removes itself from the neighbors of 2. When 3 processes itself, it removes itself from neighbors of 0. 5, 6 removes itself from neighbors of 4. And then like at that point 2, 0, 4 are on the queue. And if you see that you're trying to process yourself like 0, but you have multiple neighbors, then put yourself back in the queue at the end of the queue. Okay, I think that might actually work. So for each, I don't want necessarily a list per se, maybe. I want a set. We have a set of neighbors. Yes, a set of neighbors. So then for every neighbor process that neighbor. Yeah, I think this is fine. So when you have a node starting with your leaf nodes, if the node's already processed, skip it, add it to the process for every neighbor in the node. If the neighbor is already processed, then skip it. And then append this neighbor to the things that we want to process. I guess also, I think at this point you should check to see only process if you have like one, if the number of neighbors that are, if you have more than one neighbor, then you don't want to process yourself. So if the length of the number of neighbors to this node is greater than 1, then deck.add or append this node and continue. If so, this is going to be if other neighbors have still to be processed. Skip. I think that's right, because leaves start with nodes graph, with one in the graph of that node. Okay, so for every neighbor, if the neighbor is, I don't know that you actually need this anymore, because what's going to happen is for every neighbor in, you're never going to actually process, and I don't think this is necessary. Likely unnecessary. I'm going to check that later on. Unnecessary. So you're going to append onto the queue the neighbor. You're also going to remove from the graph of the neighbor this node. Yeah. And then you're going to update things that need to be updated. Hopefully this doesn't go infinite. Now this is graph 2 again. Okay, let's look at the end here. Oh, still incorrect. Didn't crash though. So what happened here? So you start by doing 3, and then 1 is 1, 7, 2 has a neighbor, and then 5, 4 should have a neighbor. 0, 1, 2, 3, 4. Yep. 6, 4 should have another neighbor. 0, so you should be skipping 0 because 0 still has to be processed. 2, you should be updating 0 to now have 2 neighbors. And then 4 should be updating 1 to have 2 neighbors. 1 to have 1 neighbor at range 1. Yep. And then at that point should be 0. Now you have a chicken and egg issue. If you do 0, then you say that 1 has 2 neighbors. Interesting. Actually, maybe I'm doing my leaves incorrectly, right? When I process a leaf, for instance, I have a process 3, I should be saying that the number of neighbors to that leaf is also incremented. The number of things that are next to that neighbor, that are one way from that neighbor, is incremented by 1. By default, I guess. So, because there's only one neighbor node, oh, that's not right still. This is not right still. Because when I pop 0 off the last time, I need to, yeah, it doesn't do the reverse correctly. So, like 1 could have some number of neighbors to 1, that when I do it this way, it doesn't go the reverse. Doesn't go the reverse. 7 does 2, 2 does 0. Ooh. 7 does 2, 2 does 0, 3 does 0. So all contributes inwards. I guess it doesn't matter if I go the other way. No, it does matter. It definitely does matter. Go inwards, and then I need to go back outwards to count. So like this, the 7 never actually fully gets the counts of the things that are its neighbors. So I go 7 to 0, or 3 to 0, 7 to 2, 5, 4, 6, 4. And then it could be something like 2 to 0, 4 to 1. And then at that point goes 0 to 1. I wonder, can I just do in reverse of the order of processing? So if I go 1, so I correctly got 1. stuff for 1 as the final thing. Like 1 should have 2 neighbors. And then I need to go reverse and do 0 now 0 now getting stuff from 1. How do I know which of the neighbors? So 2 contribute to 0, 3 contribute 0, 0 contribute to 1. So 1 is kind of fully correct as the last head of the tree, I guess. Then I need to go backwards and say to 4 what 1's contribution was to 4. And then go backwards from 4 to 5, what's 4's contribution to 5 is. So I have another reverse traversal. Seems like the recent problem of the recent hard problem, like the directed graph thing. And that boils down to having a stack. Where the stack is the stuff that you've processed, kind of, versus, or entered versus exit. So when you exit, you do the reverse of when you enter. So when you exit, you kind of are done and exit the node. Then you affect the nodes that are you affect the neighbor nodes that are not the single last node that's been processed. Okay, so I think maybe the process should be a list. I need to do the reverse order of that list at some point. In that case, that might be a stack. Well, so there's a process set and a process stack. I'll call this P stack for process stack. So when I process, then I add it to the stack as well. So P stack.add node, append node. I need to do this in reverse order at some point, so that's why I'm doing a stack here. So this thing goes forward. This thing goes forward to have a correct result for basically guaranteed the last number, the last thing that's processed, which is 1. Oh, why is popping 1 happening twice actually? Process 1, done 1, popping 1. Okay, this is just skipping this one actually. Because so we're done. Okay, so while there's a process stack, then the node is equal to the process stack.pop, and then for every neighbor in the graph of this node, if actually, so what I want to do here. So I have a stack. I need to remove this node from the process stack. So node processed dot root discard, remove, discard. Okay, so for every neighbor in the graph of this node, so I finish going to 1, I start with node 1, and then for every neighbor of this node, so like 0 and 4, I need to contribute to 0 the stuff that is from 1. Oh, shucks. But the stuff that's from 1 includes 0. Fuck. Oh, the stuff that's from 1 includes 0. I guess maybe that's actually fine in some ways. So the stuff that's 1 away from 1 should contribute to 0. The stuff that's 2 away from 1. Actually, the stuff that's 2 away from 1 is already included in 0. Stuff that's 2. So the stuff that's 2 away from 1 could already be included in the stuff that's 1 away from 0. Technically, these stuff are the new stuff. Ah, shucks. So 0, so this counts as 1, 2, 3, 4. So this is 4 away from 0. Actually, so let's say these two are 1 away from 0, which contributes to be 2 away from 1. 2 away from 1. Currently there's 4 things that are 2 away from 1. 1, 2, 3, 4. These two aren't known from 0's point of view. So 0's point of view, it should add the stuff that is should say that the stuff that's 2 away from 1 is going to increase the stuff that's 4 away from 2 away from 1 is the stuff that increments stuff that's 3 away from 0 minus the stuff that's 1 away from 0. Because it doesn't want to duplicate. Does that always work correctly? Seems a little convoluted to always work correctly. Like what if seems a little convoluted to always work correctly. But maybe it is correct. Stuff that is stuff that is 1 away from 1. So this 2 should increase the stuff that is 2 away from 0 subtracted by the stuff that is 0 away from 0. Okay, fine. I think it might work. For every neighbor in the graph node, and then for every way in the range of k minus 1. Not sure if it's k minus 1 at this point. It might be k minus 2. If the connected to this node of this away is equal to 0, then skip it and just keep on breaking. Connected to this neighbor at away plus 1. Okay, so the left that's 0, the stuff that's 0 away, I think maybe it should be aways 1 away. Starting with 1 away, because away of the node, away connected to the neighbor 1 away should be incremented by 1 at this point. And then for everything that's bigger than that, so like 2 and onwards, it should be incremented by connected to this node, away, and so we're doing things that are 2 away. So away is 1. If it's 1 away from this node, then it's 2 away from this node. So 2 away from this node subtracted by the things that are connected to this neighbor node, away minus 1. So things that are 1 away from this node, or let's say the things that are 2 away from node 1, which are like 1, 2, 3, 4, that increases things that are 3 away from this node. So 1, 2, so 3 away is this thing, subtracted by the fact that this is already duplicated, counted. Okay. Okay, so I think maybe that works out. You have the stack. Every neighbor, you contribute in the reverse order this thing to the neighbor, and then you keep on going down the stack, downwards in the tree. I think you also need to pop onto the stack this neighbor. Piece. No, the neighbor's already in the stack. So I think that's actually maybe graph 2. Graph 2. Oh shit. I actually removed stuff from the graph, didn't I? Fuck. So I have to recreate the graph. Yeah, I think I may have to recreate the graph. Is that right? Oh shoot. I feel like I skipped out some ideas. Let's index out of range. On line 55. For every neighbor in the graph 2 of node, if the neighbor don't actually want to do this thing if the node is no longer in process actually. I think. But why is this crashing here? So does one last, and then it removes from the process one. So actually for every neighbor, if the neighbor is not in processed, so that's something that's still to be done, then skip it, or has already been done. This is still gonna crash, but still more correct. List index out of range. Connected of neighbor plus equals 1. Ooh. Here k is equal to 0. K equals 1. Yeah, k equals 1, so it starts at 0. I guess if you have k equals 1, what can you do here? You don't really care about anything. Should this be k plus 1 up here? If it's k equals 1, then the result is always 1, no? Things that are 1 away. That's not true. If k equals 1, then the result should be like 2. Oh, it's answer I. Fuck. I could always make this k plus 1. Just have an extra layer. What's this most straightforward way? I'm reaching my end of my brain power of thinking straight, I think. Connected neighbor 1 away. I think it should be, let's say minimum of k is 2, or maximum of 2 and k. Just to make this still out of bounds. Connected neighbors of 1. Out of range. Connected neighbors at 1. That's my range. So I assume that it's not the one that's at fault, but I could be wrong. This index out of range. I think it's probably the name. No, that's right. This is should be max. I want to make it max. Okay, so it didn't crash, thankfully. So is this finally the correct thing? From 1, or from node 0, there's 1 away, and like 1 distance 1, 3 distance 2. 1 it's 1 and 2, 2 it's 1 and 2, 3, it's 1 and 1, 4, it's 1 and 3, 5, it's 1 and 1, 6 is 1 and 1, 7 is 1 and 1. Okay, let's do one more. Let's do case 3 here. Test case 3. Alright, so from 0 it's 1, 3, and 2. Excellent. From 1 it's 1, 2, and should be 4. Yeah. 2 it's 1, 2, and 3. 1, 2, and 2. From 3 it should be 1, 2, and another 2. From 4 it's 1, 3, and 1. 5 it's 1, 2, 1, 1, and 2. 6 is 1, 1. Uh-oh, SpaghettiOs. 6 should be 1, 1, and 2. That's incorrect. So close to being fully correct. 1, 1, and 1, 1, 2. 1, 1, 1. So close to being fully correct. I think maybe it's the fact that the leaves don't actually fully work with each other for some reason. Why didn't the leaves work there? Let me double check here. Wait, did I count that wrong? Oh, okay. Oh, I did count that wrong. Sweet, sweet. 5 is 1. 5 is this one. 5 is 1, 1, 2. 6 is 1, 1, 2. 7 is 1, 1, 1. Okay. Okay. That actually works. Okay. So at this point, it just needs to be. I think this just needs to be a helper method, to be honest, because you're doing the same thing on each tree. So, you're doing the same thing on each tree. So you should probably just get it for, yeah, you should probably just get an array for each tree. So let's say how to code that. The hard part and then the harder part of having to create a helper method. Oh, Jesus. So define a let's say tree tree counter, and let's pass in the edges that we want to use, the k that we want to count with. I'll say k, and let's pass in the connected that we want to use, or let's return the connected that we get from it. Yeah, we can return the connected. We can return just the array. I think we can just return the array. Syntax. Okay, so we say, I'll say E is the number of edges. This is going to be, I think it's going to be a good exercise for me to rewrite some of this code that I had down here, up here, to solidify it in my mind. So we start with the graph. That is going to, a default dictionary of sets. I think maybe I can optimize here and say it's going to be a list of sets. So set times, I don't know if I can do multiply because I don't know if it's unique sets at that point. Maybe this is actually a place for me to learn some Python. If I were to have a graph that is a set multiplied by, let's say, 3, and I say graph at 0.add 1, and I print out the graph, does it add 1 to identically? Is the same reference? Or can I just not do that because I can't do set times 3? Okay, set for something in range 3. I think this way should probably work. Yeah, it's going to be 1, empty, empty. Okay, so the graph is an array of sets for the graph is going to be an array of sets for each thing in the range of the number. Okay, I say n nodes, num nodes. I guess I really don't use this variable all that often, so I can have a wordy variable name. So for every graph, the graph is a set for everything in the range of num nodes plus 1, plus 1. What's going on here? And then I start by going through the edges and adding it to the graph. Graph at A dot add B, graph of B dot add A. Man, if I end up actually needing to do other code besides what I think I need to do for this helper, I'm going to be so upset. I don't think I need the max count quite yet. So then I created deck, double-ended queue, and I create the connected matrix. Which is for every node, the number of things that are some number away from it. It's going to be a matrix with dimensions, nodes, and range away. So it's going to be connected, and because I want to be able to at least do the neighbors at least once, even if it's not necessary for certain values of k, it's going to be at least 2. For blank in range, the number of nodes. Do I need to start out by saying it's going to be 1, 4, 0 away? I think that's still fine. So for every node in range of the number of nodes, the number that are connected to it, at range 0 is 1 itself. That's fine. And then for every neighbor, for every node, so starting the queue with the leaf nodes. So for every node in the graph, if the length of the neighbors of this node is 1, which is a leaf, append that to the deck. I'll have a processed set and a process stack. And this is needed to reverse traversal at the end. There's probably more efficient / elegant ways of doing this, but whatever. So while there's a deck node, pop it from the deck, and if the node is already processed, then skip it, because sometimes if you go through the traversal and you have certain leaves, they're going to add the neighbor nodes, and the more than one of that node might exist in the queue. And then, yeah, so skip nodes that have multiple other nodes to be processed, multiple neighbors to be processed. Neighbors to be processed. Push to end of queue. So if the length of the numbers of neighbors of this node is greater than 1, then deck.append this node and continue. Okay, otherwise we're going to add it to the process stack, process set. Process.add this node, process stack.add or append this node. And then for every neighbor in processed, again, I think that was not necessary. I think all the neighbors at that point should be all the neighbors at that point is going to be a limited list because you're removing neighbors from the thing. So I think there should only be one neighbor. There shouldn't be a for loop, really. No, that's not right. That's not right. Well, is that right? The length of so here there's only one node left in the graph. So yeah, there's only one node left in the graph. So can you do set 0? Can you do set 0? Let's say so I have a set here. Say temp is a set. Temp.append or add 10. Can I do temp at 0? Learning more Python that I'll probably forget. So I can do temp at 0, okay, even though it's a set that I'm indexing. Oh no, I can't do, I'm doing temp. This is gonna crash. Yeah, it's a set. So how do I return the only element of a set? I forget how to do this. Return only element of a set. You can use the next function. Retrieve any element from the set. I don't want to do all this stuff. Next on the iterable of my set none. To return the only element set, you can use the next. This approach is efficient and concise. The iterator functions creates the iterator of the set. I don't want to do that. Now extract the member from a single member set. Tuple unpacking works and verifies set contains only. My personal favorite for getting arbitrary element when you have an unknown number, but also works if you have just one. Tuple unpacking verifies the assumption that the set contains exactly one element, raising value error. So element, comma, blank, my set, or equivalently without requiring the trailing comma. Between making a tuple and making an iterate is almost a wash, but iterations wins by a nose. Not sure why all the answers are using older syntax, iterate x dot next rather than the new one, next of iterate x, which seems preferable to me and also works in 3.1. However, unpacking wins over both hands down. What's unpacking wins both hands down. X is equal to the set. This is a force. This force is for single item sets. For sets with arbitrary, it slows down. X equals set bracket 1 close bracket. Is the stuff inside the bracket representing, is that a 1 or is that an L? What is that? Is that a 1 or an L? I think that's a 1. Set parentheses bracket 1. Does the 1 represent the number of elements that you're using? X equals set bracket 1. A is equal to O. Okay, so okay, this is the actual thing. A comma whatever is equal to X. Okay. So it should be something like print, or let's say X A comma equals temp, and print out A. That should work. 10 is A. Okay, so I don't know if I'm going to remember that, but something I learned for this exercise. So where am I at? Kind of lost my train of thought. I appended the stack Oh yeah, I think that there's only one thing in the graphic node at this point within that set, so I don't think I need a for loop here because there's a single neighbor. So deck.append the neighbor. So I can say here the neighbor is equal to the single thing inside the graphic thing. So neighbor equals neighbor comma equals the graph, this node at this point. So single neighbor at this point. Okay, and then what do I do with that neighbor? I say if the neighbor is to be processed or process continue. I don't think this is necessary. So I start with the leaf. The neighbor goes to its single neighbor. So it shouldn't have been processed at that point. So I don't think this is necessary. So then deck.append the neighbor, graph2 discard the neighbor. Okay. So deck append the neighbor, graph this node dot remove or discard, doesn't matter. This node from the graph of the neighbor, discard this node. And then for every away, this part I'd probably copy. Maybe for every away in the range of k minus 1. Okay. For every away amount in the range of k minus 1. If the connected to this node of this away amount is already just 0, then I don't need to worry about it anymore. Otherwise, then connected to the neighbor one away, one more than the way amount is incremented by connected to this node at this away amount minus there's no minus in this one, it's just added, right? Yeah, this is the forward version, so I just need to add. Okay, and then I'm done with that first part. And then I need to recreate the graph. I wonder if there's a better way of doing this, like removing, creating, removing again. Probably doesn't really matter. Actually, I wonder if there's a faster way. Copy sets in Python. How do you make a copy of a set? Copied set. To copy a set, the copy method or the equals operator can be used. Copy creates a shallow copy while the equals operator creates a new reference to the original. Copy method creates a shallow copy. Yeah, so modifying the copy set does not affect the original set if you make the copy method, and equals is just using the same reference, right? Modifying the copy set also affects the original set. So I can do dot copy rather than, so I need to do the copy here. I need to do the copy up here. Copy equals, let's say graph copy. is equal to graph at k dot copy for k in range of num nodes plus 1. Is it num nodes plus 1? No, it's just num nodes. I already fixed the plus 1 up here. I didn't. Yes, m, where m is that thing plus 1 already. Okay. And then, so I have my graph copy. So I have to do the whole edges thing again. And then I'm going to go ahead and just set the graph to that graph copy. Graph equals graph copy. Okay, so that's this part. And then while there's a, no, what did I do here? So yeah, that's this part. And then I do the process stack. Okay. So while there's a process stack, pop from process stack, discard. While there's a pstack, node is equal to pstack.pop. If the node is, if process discard the node. And then for every neighbor in the graph of the node that's not processed, for every neighbor in the graph of this node, if the neighbor is not in process, then continue. Otherwise, the connected to the neighbor that one away is increment 1. That's this node changing the number of valid neighbors to it. Neighbors to the neighbor. And then for every away, in range of 1 to k minus 1, skipping over the 1, if connected to this node at this point is equal to 0, then just stop. Doesn't need to bother. And then connected to this neighbor, away plus 1 plus equals connected to this node at away minus connected to this neighbor away minus 1. I think that's all right. And then we return, what do we return? We return the connected, the last. We return the last array within the connected matrix, the array for each node at k away. So is that a single row? So the matrix has rows of nodes and columns of each range amount. So I think I want it to be something quite slightly different than that. So the answer is going to be connections, or it's going to be a list created from connected at node exactly k away. So k away should be k minus 1 here, we'll say. Did I actually use k or did I use k? This is wrong. This is supposed to be graph the variable k. This is horrible. I shouldn't have used the same variable with different spellings. This is a bad idea. Holy cow, that's a bad idea. So hard for me to debug at that point. Like I'm reading to myself the same letter. I'm trying to figure out that I'm referring to two different things. All right, lesson learned. Okay. Connected to the node at k minus 1. Is that right? Time for k. Oh my lord. Okay, connected to node n a away in for no, actually a is actually a constant, which is k minus 1. But n is a variable for n in range of the number of nodes. I think that's right. So I want to list for every node basically the last column of the matrix. I think. Okay. So let's go ahead and just say array is equal to my help method, which I called as tree counter, passing in edges 2 and let's say k right now, and I'll print out the array. This is crashed. It's probably gonna crash. Deck is not defined. Okay. Did I delete? I think I might have deleted stuff here. Yeah, I probably deleted stuff. I probably copied and pasted for some reason. Or cut and pasted. Deck is the double-ended Q. This indices length of the graph of node equals 1. This indices must be greater than, must be integers or slices, not sets. Length of the graph of node. Really? Line 21. Didn't I have something exactly like that in the other part? Length graph of node equals 1. For every node in the graph. For every node in the graph. Oh, I changed it to be a 2D matrix. Okay. Or I changed it to be a matrix rather than a list. So I can't go through this way of getting nodes. For every node in the range of the number of nodes. Yeah. If graph of that node. Okay. So I do that same. I don't think I had the same issue afterwards, maybe. Not enough value send back expected 1 got 0. Unfortunate. Okay, so I thought it'd be a single neighbor at this point. And it should be a neighbor. But it says expected one got 0 neighbors. Hmm. When would they have 0 neighbors when I'm processing this stuff? Alright, I think maybe this is a little too fancy. You say for every neighbor in the graph node. I think that's still totally fair to just assume. Or just to be able to do. Even if it mostly it's going to be one neighbor. Okay, so let's see if this thing... So this thing gave me something that's incorrect, I think. Ooh, baby. Huh. Oh boy, it doesn't match what I previously had. Yeah, so 0 is 0, it should be 3 and 2. I think I must have messed up not only did I mess up something, I actually deleted something in my code. Oh boy. So, Yeeks. 2, and then this thing's giving me something that's not even matching. 2, 4, 2, 2, 1, 2. Why is this giving me 4? Like 4 is that number. The 2 is like this number. Maybe I'm actually... Well, the printouts are still from the previous stuff. So did I screw up something with the... Shucks. Appended it. I thought this would still be the same code up to here. Actually, let's go ahead and print out. I didn't actually print out the piece that connected anymore. The connected is still fine. Okay, yeah. And then 2, 4, 2, 2, 1. Okay, so this is actually fine. Okay, yeah. Actually, this is all fine. So the array that I get back from the call is actually what I want. I think I can comment this out rather than delete. So I have something I can go back to if I massively fail the conversion. Okay, so I don't need this stuff here. So I have my tree counter helper method, and I can say my array1 is tree counting the edges of the first tree with what is answer? Okay, so the answer is just an array. Okay. Tree counter 1 for the original k amount. Is it for the original k amount? Yeah, it's for the original k amount. I need to go 0, 2 away from 0 in the first tree. So k amount 0 from the first tree. And then for the second tree, I want just to be k minus 1 away from any node there. And then the answer array is going to be for every value, actually, it's going to be a fixed amount from the max count, or max away tree 2 is going to be the maximum of the array 2. And then, actually, it's just everything plus that max away for, so I think it might be value plus max away in tree 2 for every value in array 1, return like a return answer. Oh no. I was really hoping that worked. Okay, so let's go ahead and print out array 1, print out array 2. Okay, so I think I need to sum it up, right? Because the number of things that are a certain number away is the sum of those things. Is the sum of the things that are 1 away, 2 away, 3 away. Okay, so I think my tree counter should be returning a matrix that is the sum of the columns, or the sum of the rows for each node. Yeah, so let's go ahead. Let's go ahead and say that where is the return value? Okay. For each node connected, it's going to be the sum of the connected of that node. That's it. Okay, so okay, so if I have k is 2, the sum of the nodes that are connected to this thing that's 2 away. Uh, 5, 3, 5, 4, 4. Let me do the test case here. Should be case is 2. I think it looks like it's maybe off by 1. Because I think if I did 3, it actually gave me 97988. Yeah. So it's like 97988. So it's like off by 1 for some reason. So this thing is off by 1. Sum of the things that are connected to n. Maybe this should be k plus 1, and this should be k. No sir, no sir. Okay, let's try case 2 as a test case though. Okay, so it worked for k equals 2 here. It stopped working when k is 3. K is 3, so stop working. So it's 11, 11, 12, 11, 11. Okay, so when k is 3, from 0, 1, 2, 3, 4. It should be 5 actually. And from 0 it should be 1, 2, 3, 4, 5, 6. So this part is right, this part is wrong. 1, 2, 3, 4, 5. That's only saying 4. It should be saying 5 for each of these. Okay, so why is that? Okay, so time to do some more printouts. So I think I want the printouts inside the loop. Inside the does it make sense to see it inside the first loop, the second loop, possibly the first loop? So while there's a deck, let's say print the node process node, and then maybe at the end of it print out fact. So while the deck exists, print out post and what the queue is, no, what the connected matrix is. Okay, so we start by processing node 1, which is a leaf. And you say that node 0 now has a neighbor. And then you do process 3, which is leaf. You should say that node 2 has a neighbor. Go 4, and you say 2 has another neighbor. You go node 0, and you say that 2 has another neighbor, and then it has a neighbor that's also 2 away. At that point you do node 2. Node 2 is the last one. And you reverse the process. So you start with node 2 that has 1, 3, 1. So node 2 is 1 away from itself, 3 away, or 1 away from 3 things, and 2 away from 1 thing. And then you're processing node 2, but that really doesn't change anything. Okay, so that seems fine for the phase. And then the second phase is, actually let me go ahead and for now remove array 2 from consideration. And then while pstack process, so let's say here print second process in this node, and then after all this print post second process for this node, actually what the connected is. Okay, so process 1, 3, 4, 0, 2. Alright, second process. Oh baby, negatives. Oh no. Oh no, 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 no. Negatives. Oh, that's not good. So what's going to happen here? So if you do the second post process, so say 2, so for each neighbor 2, so like 0, 3, and 4, you're somehow saying that 0 is now 1 away from itself, 2 away from 2 things, 2 away from 2 things. It should never get to this phase. This should be just 0. So if the connected away should be 1 or more. So how did this thing become -1? Connected node at away, and then connected with a neighbor away -1. So if it's changing this node, then I think it's looking at k at away being 2. So at away being 2. So it's subtracting the number of things that are 1 away from. I think, is it doing the wrong order? So like it's increasing the things that are 1 away from 0 to be 2, and then using that same value later on incorrectly. Yeah, I think maybe this is the fact that I should be doing this in reverse order. So if I do it in reverse order, then I can't do breaking at 0. So for away in range 1, yeah, I think this probably needs to be k minus 1 going down to 0, not including 0, -1. And then if it's 0, then just continue. Not quite pass. Oh, jeez. Broke some more. Okay. Out of range. I think it might be k minus 2 at that point. Because you can't do can be at most k minus 1. Yep. Okay, well, no longer crashes. Still give me negatives. Oh, okay, so that's not the way to handle this. So initially it's fine, or at least initially there's no negatives. So when it processes 2, where 2 has one thing away from itself, 3 things away from it by 1, and 1 thing away from it by 2. This is majorly off. So 0 is the neighbor of 2. Things that are 1 away from 2. Okay, so let's think about this. Things, so it would start by doing k minus 2, which at that point is going to be, well, k was originally 3. So 3 minus 2, but I call it k plus 1, so passed in, this value is 4, 4 minus 2 is 2. So it starts with 2. So connected at 0, 2 away. No, sorry, node 2, 2 away. Node 2, 2 away. Node 1, node 0, 1, 2, 2 away is 1. So neighbor at 4 at that point. Neighbor at 4 at that point is going to become, isn't that out of bounds? So away is 2, so connected at 3. 0, 1, 2, 3. Connected at 3 is going to be 1 minus connected a node away, 1 minus stuff that is, let's see, stuff that's 2 away from 2, so subtract stuff that's 1 away from 1. I see. This thing is, even though I did this in reverse order, this thing is done first. Wonder if this is even necessary at that point. I think I might actually don't want that. Okay. Still incorrect. I guess. I guess there was a reason why I had this, because the stuff that is 1 away from when it does 1 away from that neighbor, it never actually takes into account. So I think maybe even though I delete it there, I still might want it to be done here after everything. 5, 5, 5, 5, that is I think what I'm looking for. Okay. Okay, so let's go ahead and just remove some of these prints. And return the array. The modified array. Okay, so still wrong answers. Okay, so what's going on here? 74444 versus 63333. Huh, interesting. Interesting, one away. Okay, let's go ahead and put back. Let's go ahead and put back the comments. Okay. Right, so the first process, it's only going for 2. So, I did the sum of everything, and k is not necessarily everything I want. Okay, yeah, this is one where I need to actually figure out how to do this with not min or max 2 from k. Okay, I think this is, I need to change this to be actually k, and here I say that if k is greater than or equal to, if k is greater than 1, do this. Okay, let's go ahead and put back in the return. Array 2 not defined, probably uncomment out the comment. Lord. Oh boy, oh boy, oh boy. Test cases finally passed. Now let's see if it actually does the whole enchilada or part of the enchilada. I think I still have another printout somewhere. For some reason, when I try to submit, it seems to double submit. Index out of range, number 15. Okay, this is probably like a stupid k equals 0. Yeah. If k equals 0, then am I guaranteed nodes? Am I guaranteed nodes? The number of nodes is guaranteed to be 2. So if it's 0 away, then it's just 2. 1 from the first tree. Well, actually, it's just 1, right? It's like just count itself, and that's it. Is that the correct answer for that? If k equals 0, what is the expected return? I'm pretty sure it's supposed to be returning 1 in that case. It's returning 1 for every possible thing. Turn 1 times the number of elements in edges 1. Is that Is that not how you would do it? Maybe as a list like that. That's probably still not correct, is it? So if you want a list of ones where, it's odd. I guess it doesn't know. Oh, whatever. One for whatever in the range of the length of the number of edges. Okay, that should definitely work. Gosh damn it. Length of edges is 2. How do you get a list of ones? What? Python create list of ones. I thought I did that. 1 times n. K equals 0. 1 times the length of the number of edges. What's going on here? Expected is 1, but I only got 1. Right. This is edges plus 1 again. God damn it. Length of the number of edges plus 1. Ugh. Okay. I swear I am only pressing it once. Please. Holy bejeebus. That was so hard for a medium. That was so hard for a medium. I mean, I feel like I deserve this, but oh my god, that was hard. Oh my god. And I'm guessing I did a solution that was fairly different than other people. Oh, Lord. Oh my Lord. Holy jeeps. Okay. Time to tidy up and then go through the end of this deal. Moving the comment out print stuff. That's moved. That stuff's removed. I think maybe inside this thing is there. All this stuff is gone. Okay. Turn max. Okay. The only variable is how much reaches. Double checking here. I didn't do something stupid and delete something necessary. Okay, so there's just no way this is a normal problem. I don't know. So the summary of this one is so let's see, by logic, assume that the second tree connection, so because of the way this problem works, it's always going to, the placement of where the first tree connects to the second tree to maximize the range of the number of connections from that node in the first tree, it's going to be a fixed amount in terms of it should always connect to some maximal node in the second tree, and every other node following that connects to that same node. So what you're really concerned with is not like trying to optimize two different trees here, but it's basically the same problem. You're trying to figure out the best node in the second tree, and for every node in this first tree, what the range from that node is. So really, if you create a single function that determines how many nodes are within k range of a given node, that function can work to can answer the question, since the function for the, let's say, graph 1, that node, since the number within k of node 1 in graph 1 equals function for that node in graph 1 plus the function with k as the range plus function of graph 1 of any node that is k minus 1 away. So this second part is constant, but you still basically need to figure out how to determine how many nodes are connected to a given node at certain k range. And so I broke this down to create, so you need to calculate for each node how many nodes are 0 to k away from it. So this is the matrix where this is a 2D matrix where dimensions are nodes and away range. And here the steps to calculate matrix, and it's not easy, or wasn't simple at all for me. One was to, obviously you need to create some data structure for the graph, and you can use the default dictionary of lists, which is what I usually, here actually I said default dictionary of sets, or an array of sets, where sets are connections to node, and then you traverse graph starting from leaves, and here you need to detect leaves by going through nodes. Okay, actually, so start with an empty queue, add leaves to the queue, and you can detect leaves in the graph where the length of the graph at that node, the length of the set or the list, or however you want to do it, is equal to 0 or equal to 1. And then process queue starting with leaves, where when at a node change the matrix for its neighbors depending on the connections for that node. So that was this step right here. So once I created once I had a leaf, right? And I'll say what happens with the non-leaves later on, but once I have a leaf, then I look at the neighbor to leaf, and for each neighbor, I change the matrix for that neighbor. So the number of connections for the neighbor that's one away, so the range is one away, or the range is sum plus one away is equal to, that's for a given node and a certain away amount. So like let's say the things that are one away from this current node, it's going to increment the things that are two away from the neighbor node. Or the things that are two away from this node is going to increment the things that are three away from the neighbor nodes. So it basically does that contribution, but it does it in a way that it doesn't duplicate the contribution, because you're doing leaves to root and you're not doing some mishmash of roots and leaves. So the leaves are contributing to the roots in an orderly fashion when you do this queue. So process the queue starting with the leaves, and then remove during process, remove node from list or from set of neighbors of that neighbor. So they eventually become leaves themselves. And then before checking neighbors, confirm node is a leaf, and if not, then add node back to the end of the queue. And that's to prevent it from processing self before it does its neighbors. And then this process only does one way. It goes forwards towards the root. And so once it does forward towards the root is correct, but then technically the leaf nodes are not correct, because the leaf nodes are only contributing the stuff that they only have stuff that's known to them that's below them but not above them in the tree. So since the above process only correctly contributes to the range, the stuff below a node need to do the reverse calculation of how the stuff connected to the roots, the nodes connected to the roots, affect the connections for the leaves, the nodes that are below it. So this is doing so keep a tracker of which nodes are processed and the order of processing, so that in the second portion go through the reverse nodes and provide to do that extra calculation. So that was the second. Stack rather than a queue, because you're starting with if you do the processing, and while you process a node in the first queue, you want to do it in reverse order in the second queue, so that the last thing that you processed is the last thing that's on the stack. So that's the first thing that you kind of contribute to its neighbors. Note that there is a very tricky, in my estimation, calculation where you don't want to double contribute the things that are within range X. So things that are within range, let's say 1 of this node, would be things that are actually, so let's say I want to contribute things that are, I want to figure out things that are 2 away from this thing, right? And I've already figured out things that are 1 away from this node. This is like the root. Things that are 1 away from this node is actually including things that are 0 away from this thing, or things that are 2 away from this node, which are these two. And these two are including things that are 1 away from this thing. So like k away from this node is going to affect k minus away. K might include things that are k minus 1 away from this other node. So there's, you need to subtract that out. Subtract that out correctly. So that was this thing right here. The connections of the neighbor that's 1 more than k away, or some away plus 1, is connected to the current node away by 1, or away by itself, and the neighbor node away minus 1. So yeah. And then, lastly, determine answer using sums of the things that are 1 or k up to k away from nodes in graph 1, and maximum of sums for any node up to k minus 1 away in graph 2. Calling helper functions appropriately. Alright, I don't know, it's been like probably 3 hours. I'm so tired. Time complexity for this is going to be O of, so you need to iterate through every node, every edge, and for every node. So it's like maybe number of edges plus node times node times k plus m times k, where n and k well, the number of edges is based on the number of n and k, so n and m are number of either nodes or edges, because they're just 1 away from each other, or each, for graphs. And since you're going through basically every node and then every edge, processing every edge for every away amount, Actually, let me think about that. Is it n squared for every node? Do you process an edge more than once? For every node, you go through every edge, but the number of edges is capped to be the number of nodes. I think that's correct. It's n times k. In space complexity, you need to have n times k for the for both the graph, which is the set of edges is O of n really. For the graph, because there's going to be at most, yeah, maybe n squared. Let me think of that. So 0 has 1, 2, 1 has 0, 4, 3 has, there's no cycles in it. And each edge contributes to 2 elements in the sets. So for the graph, so this is the list of sets, and O of n times k plus n times k. I guess it's O of n plus m for the graphs, and n times k plus n times k for the matrix of connections, of connection counts that you're tracking in the in calculating the overall range. All right.